Okay, I'm going to go through the second part of this Pearson Edexcel IGCSE Physics Paper 1 run through. I went through 3 questions in part 1, all to do with forces, so I in fact covered questions 1, 3 and 5. Okay, so I'm going to go straight to number 2, question number 2. So if you haven't watched the first part, go back and take a look, and to show your appreciation, don't forget to like every video that you find helpful and share it with your friends, because I'm getting more requests for A-level compared to GCSE, so if we want more GCSE videos in time for your exams this summer, make sure you give me requests, and I need to get enough views and likes and subscribers to make it worth my while. Otherwise, I'll do mostly A-level papers instead. Okay, so this question is about topic 6. So topic 6 is on magnets and electromagnets. Okay, it's got a diagram which shows the magnetic field between the poles of 2 strong bar magnets. Okay, well, we can't see the full bar magnets, so they want you to add labels to the diagram to show the poles of the bar magnets. Now you should know, if you revise this topic, that the field lines always go from north to south. Okay, so you can see the field lines are going this way, so that means that you know this is the North Pole and this is the South Pole. So that's going to get you your first mark. Okay, the next part of the question says the bar magnets are made from steel. Okay, now if you've revised this topic, you know that there are only 3 elements which you can make magnets from: iron, cobalt and nickel are the only magnetic materials. Now steel is magnetic because it's made of iron. So steel is an alloy of iron with carbon. Okay, so the question now they're asking you is, give one reason why steel is a good material for making bar magnets. Now these bar magnets are permanent magnets. Okay, and steel is a hard magnetic material, whereas iron is soft. The fact that steel has got impurities in it, iron with carbon mixed together, it's what changes the properties of iron into steel. It's hard to magnetize, but it's also, once it's magnetized, it's hard to demagnetize. That means it stays magnetized once you've made the magnet. So that's why steel is a good material to use, and that will get you the 1 mark, is knowing that it's called a hard magnetic material, and in brackets I've explained what that means. Okay, the next part of the question says, explain how diagram 1 shows a uniform magnetic field. How do you know it's uniform? Well, if the field lines are straight, parallel, and equally spaced, that's what we mean by uniform. Okay, they've got to be straight, parallel, and equally spaced. So the mark scheme is looking for these 3 points for the 2 marks. Okay. So magnetism is really quite simple. Well, we did question 1 already. Here's the second part of question 2. I think I flipped the pages back to front when I PDF'd it. Okay, so next part, it says diagram 2, yeah, shows a metal wire being moved downwards through the uniform field between the poles of the same bar magnets we just looked at. So here's a 3D image. So this must be the North Pole, this must be the South Pole. Okay, if they haven't changed it. So it's the same ones. So you're going to move this wire, and a wire is a conductor. They've told you actually that the orientation of the magnets has not been changed. That means you've got the north on the left and the south on the right. Okay? Now when you move a wire, so the whole thing is the movement of the wire through the magnetic field lines. They haven't drawn the magnetic field lines. It is called electromagnetic induction. So when you move a conductor, all the electrons which are free to move, so the free electrons, feel the magnetic energy between the north and the south pole, if you like. So that causes them to move one way or the other through the wire. So it produces a voltage, okay? And this is what the question is going to ask you about. Give a reason why a voltage is induced, okay, between the ends of the metal wire. Okay, so if you put a voltmeter, let's do that. If you put a voltmeter across the ends here of the wire, it would show you how much voltage was produced. Okay, so that's basically what electromagnetic induction means. Okay, so between the ends of the wire, as it moves, oh, I'm on the wrong functionality, as it moves between the poles of the bar magnet. If there's no movement, the voltage will stop. It's actually because the wires are made of conductor. The wire is cutting through the magnetic field lines. And it's that cutting through, imagine the field lines that we showed you in the first part. You're actually cutting through them. So you need to cut through them at right angles. And all the free electrons feel that there's a magnetic push there, and they're pushed to one side. And if you want to work out which way they'll be pushed, you need to use Fleming's rules. But I think they don't expect you to know it for the IGCSE, the electromagnetic induction rule. What they do expect you to know is how you can change things to make it stronger or weaker. So it says state two changes that could be made to this arrangement that would increase the magnitude of the induced voltage. Okay, well, if you move the wire faster, you'd be cutting through the field lines faster, and that is one of the ways of increasing the induced voltage. You could use stronger magnetic field, so you could either have stronger magnets, or you can put them closer together, because that will make the field more intense. Okay, and the third way would be to, instead of using just one wire, have more loops of wire. Basically, you're creating a coil, and it moves between the poles, because obviously each loop of wire has free electrons in it, and they all feel the force, so you've got a bigger effect, and that's what a voltage is. It's the amount of energy you give to the charge, and electrons are the charge. So that's a 7-mark question for electromagnetism. That's the only question on electromagnetism in this paper. Okay, so we're going to go straight. For A-level students, or students who want to go and do A-level, the EMF is the epsilon on the left-hand side, B is the magnetic field strength, L is the length of the wire, and V is the velocity of the wire. Yeah, and these are the things, so the E would be in volts. The magnetic field strength is measured in Teslas, you don't need to know that. The length it would be measured in meters, and the velocity would be in meters per second. So these are the 3 ways of increasing the EMF. Electromagnetic induction. Very interesting and complex subject. Question 3 went through in the first video because it involved forces and I was trying to show students how forces and energy can be linked, especially when you're doing the efficiency, work done, mechanical energy transfer, are all when forces are being used to do some useful work. Okay, so I put the mark scheme in between the questions, so all of this will be in the first video, so go back and watch it if you haven't watched it already. Doesn't really matter which way you watch the videos. So the next question we're going to go through is on radioactivity. Okay, I'm going to stop the video here and show you some of the answers, because they're asking where background radiation comes from. Well, background radiation, so question 4 is what we're looking at. So question 4, looks like my pen has stopped working. So I thought I charged it. So I'm going to have to use my finger. Okay, so question 4 is what we were looking at. And you can see in question 4, they want to know what are the sources of electromagnetic radiation, not electromagnetic, radiation coming from space. So the sun gives some, cosmic rays means rays from space, rocks, especially granite rocks, which then produce radon, yes. So this radon then collects in places where there's lots of granite. And here they said weapons testing, food, our food will have some radiation in it, nuclear disasters like the one in Chernobyl in 1986 and in Japan, Fukushima in 2011, and also medical equipment. These are all sources of background radiation. So I haven't written them all down. So when we go through the questions, we will see how many of these points you can cope with. Okay? All right, so the problem with using my finger is that when I move the page, it also sometimes thinks I want to use the pen. Okay, so topic 7 is about radioactivity, and it says a teacher investigates the count rate detected from a radioactive source. Okay, so the count rate from a radioactive source. So topic 7 is radioactivity. So my students did it recently or just before Christmas. State one source of background radiation is what they want to do. So I put cosmic rays from space and rocks. These are always the ones that I give. And then you could see the alternatives that I showed you on the mark scheme. Now describe how the teacher could measure the count rate. Yes, so we want, this is like a practical skill, how you could measure the count rate from the radioactive source and correct the count rate for this background radiation. So remember, background radiation is natural source of radiation. And if you don't take it into consideration, it's like a zero error. So it'll give you a reading which is too high if you don't correct for it. All right, so to measure it, you need a Geiger Müller tube. And the Geiger Müller tube is attached to a counter, so it can count how many radioactive events take place inside the Geiger Müller tube. And you need to use a timer to make it a fair comparison, because it says it wants you to look at the count rate. Okay, so the count rate means per second or per minute. Okay, so normally I would count the radiation coming into the Geiger Müller tube for about a minute, and that allows you to be more accurate. Okay, so the other things you need to mention, what the teacher needs to do, he needs to measure with the source and without the source. So obviously there will then be a difference. You could probably need to repeat an average or take the mean, which is a more scientific way of saying that you need to add the values up. Say if you do it 3 times and divide by 3, you're actually taking the mean average, not the mode or the median. Okay, so When you measure it and repeat with and without it, you'll see there'll be a slight variation due to the spontaneity of radioactive events, but you also need to do it with and without the source. So without, it will give you what is the average background count rate in the laboratory or wherever you're doing the experiment. And then you need to correct by subtracting the background count level. Okay, so here I've put, you subtract from the mean the background from the mean. So subtract the mean background from the mean count with the source. Okay, and if you have a look at the mark scheme, I don't know if I waited on the mark scheme for long enough for you to see. You can see how they've written it different to me or similar to me. Okay, I'm just going back to the mark scheme for this question. Yeah, so that's part 2, and part 2 I'll put in yellow. So we're looking at the 4 marks here. So when you've done your question, you can come back, have a look at this and see how well you did. Okay, part B I'm going to show you all in one shot. So part B is the next part, and you can see it's got a half-life graph there. Okay, so it looks like they've also given you some data. Okay, all right, so part B is the next part we're going to look at. So here it says the teacher places a piece of lead. Now lead absorbs radiation very well, and that's, for example, when you go and have an X-ray, you'll see that the X-ray technician also wears a lead apron because it stops them getting any ionizing radiation. It protects them a bit from it. Okay, the teacher places a piece of lead between the radioactive source and the radiation detector. Okay, so lead is a great absorber. Okay, the only thing better probably is concrete. The teacher determines the correct count rate from the radioactive source by doing it 3 times and calculating the mean. You see, they're using the word mean and not average. So the correct count rate means that they're doing it in a valid way, in a scientifically correct manner. And this is all about the scientific method, this question. Yeah, you got validity, which means that you're actually measuring what you think you're measuring, and then you're doing it 3 times and averaging, which gives you a more reliable bit of data. Okay, so they repeat this process using different thicknesses of lead. So you can see the independent variable is the different thicknesses of lead measured in millimeters. So that's the independent variable in the scientific method. And the table shows that they have their results, trial 1, trial 2, and trial 3, and then the mean. Yeah, so they are doing the count rate in becquerels. Becquerels means per second. How much activity did they detect with the Geiger-Müller tube, which is their measuring device, which we mentioned before in this question. So they've gone from 0 all the way 0 millimeters, that means without the absorber. They've gone from 0 all the way up to 10 millimeters. Okay, they're going up, so that's the range of that data, and they're going up 2 millimeters each time, and you can see they put it accurately to 2.0 millimeter. Okay, so they must have measured it with a very precise tool, and you can see how spontaneous the radioactivity is, because the first time was 480, then 504, then 469, and that's per second. So it's quite an active source. So they've then had to take the average, which gives them 484. So to cut it short, They want you to fill in the mean for the 6 millimeter because you can see that they haven't done it for you. Okay? Now, by having a range of data each time, it also allows you to estimate the reliability of data, or we could say it allows you to estimate for students going on to A-level the uncertainty in the data. So if the range is from 141 to 154, that's a range of 13, that gives you an idea of how uncertain measurements in physics can be. Okay, so they want you to, for this last bit, they want you to calculate the mean when the thickness of the lead is 6 millimeter. So if you can do it accurately, you will get the 2 marks. Okay. All right. So I haven't done it. You have to look at the mark scheme. Oh, I have done it. 148 is what I put, and you can see I haven't put a decimal place because they haven't put any decimal places in the data for the mean, and that means you mustn't put any decimal places in here. It's got to be consistent. So the 148 that you're measuring goes in there. Okay? Or you don't have to put it in there because they've got the answer space, and you can see they've done the unit for you. So it's just the calculation and whether you rounded it up. If you put a decimal place, you probably just get 1 mark out of 2. All right, so that's that part. Now they want you to use the graph paper that they're going to give you. They want you to plot a graph of the mean count rate against the thickness of the lead. Yeah, and then they want you to draw a curve of best fit. Yeah, that means you don't join the dots. It's got to be a smooth curve. Okay, so I've shown my students how to do that. Hopefully you've been shown how to do a smooth curve freehand as well. Okay, so over to the next page. So I've put my count rate on the y-axis and the thickness of the lead, which was my independent variable, on the x-axis, and I've tried to do a smooth curve in pen. It's not the best of curves, but it's good enough. You can see that some of the points are not, 2 of the points are above the line, 1 of the points is below the line, and that's what they mean by a curve of best fit. Alright, so you'll get marked on this for the accuracy of your plotting. If your plotting is not accurate, and they will check, you will lose marks. So, axes must both be labelled. Axes must both be labelled with the appropriate units. So thickness of lead in millimeters, and the mean count rate in becquerels. Remember, that means per second. So if you got the both axes labelled correctly, you'll get 1 mark. Then you've got to choose your suitable scale, and you've got to use as much of the graph paper as possible without going up in funny numbers. So you want to go up in, like what I have, hundreds on this, nice round numbers. I've gone up in hundreds, and here was obvious you're going up in 2s because that was a sensible scale. So we're looking for suitable, sensible scales. Always go up in multiples of 1, 2, or 5. Okay? Don't use 3s, 4s, any other numbers. Multiples of 1, 2, and 5 for your scale, and make sure you cover at least 50% of the graph paper, whatever scale you've chosen. And you can see that my points are 80% of the graph paper is being filled by the points in both directions, at least. So accurate plotting, then they will check if any of your points are far from the line. They'll check the points which are furthest from the line, and if you're out by more than 1 millimeter, you'll lose the accurate plotting mark. And then you draw your smooth curve, don't join the dots, and you get the 4th mark for the graph. And then it says, to carry on reading, it says, when there is not a sheet of lead between the radioactive source and the detector, which is the Geiger-Müller tube, the radiation detector, the mean count rate is 484 becquerels. So that was when the first data point, okay? Use the graph, it says, to determine the thickness of lead that you would needed to reduce the mean count rate by 25%. Well, 25% would be reducing it by 121, and that means there'll be 75% of that left. So 484 minus 121, or 75% of 484 would be 363 becquerel. So I have put where I would consider 363 becquerels to be, yeah, and I've circled it on the y-axis in green, okay? So I have done it here. There's the 363 becquerels. So I know that's what it will be. And then I see, when I draw a line from 363, now 363 is in between the squares, so they'll see how well you do it. So you draw a line going across from there, and then you draw it going down from there, and you'll see that the answer will be below 2, and you'll see that's the thickness of lead you need to drop it to 75% of the original count rate. And that's 1.8, yeah? So you need to write the thickness would be 1.8 millimeters. Now my pen's not working, so my fingers are a bit fat. 1.8 millimeter. My Apple Pencil, I need to go and charge it. Okay, the next part of the question reads as follows. A radioactive source emits only one type of radiation. Remember, there are 3 types of radiation: alpha, beta, or gamma. Alpha is a helium nucleus, beta is a fast-moving electron, and gamma is electromagnetic, highly ionizing radiation for electromagnetic waves. All of them have ionizing ability. Explain which type of radiation this radioactive source emits. Well, it's gamma. How do I know? Because alpha or beta can't penetrate lead at all. So only gamma can penetrate lead. See the word penetrate? Alpha and beta would be fully absorbed. So you wouldn't have this gradual decrease. So it must be gamma, and that's how you get the 2 marks. 1 for realizing it's gamma, and 1 for your reasoning. And that's the next question of 15 marks. Okay, so I hope you found that 2 questions, one on electromagnetism, which is topic 6, and radioactivity, which is topic 7. So we've done topics 6 and 7, and on video 1 we did topics 1 and 4. So I hope you found that useful. So you'll see when I come back and do part 3, we will go through a couple more questions. And remember, if you found it useful, to show your appreciation, give a like for every video you watch, and share it with your friends if you, whichever school you're in, and it will then be a message to me to make more videos if I get enough people watching them. Okay, so bye for now, catch you in the next video.